Hey everyone, so today we're going to be going over Newton sums. So in the previous video we talked about Vieta's formulas and the elementary symmetric sums. And so today the Newton sums are sort of like an extension or like a harder version of those formulas and symmetric sums. So before we begin, let's first do like a quick review of symmetric sums and symmetric polynomials. So a symmetric polynomial, f over n variables. So this basically just means if it's a polynomial f, which has n variables in total, is a polynomial f of x1, x2, x3, blah blah blah, all the way to xn, such that it is invariant under all the permutations. So what this means is that if you have this polynomial, this is going to be equal to f of, let's say, x3, x1, x6, n. And this is also going to be equal to, let's say you have like another like random x7, x2, x1, so on, xn, right? This means that it's going to be invariant. So a symmetric polynomial means no matter how you rearrange these variables, it's always going to be the same polynomial. So let me just show you guys with a quick example. So let's say you have f of a, b, and c. This is going to be equal to, let's say it's going to be equal to a squared plus b squared plus c squared. So then, if you were to switch it around, right? Like if you were to switch around the ordering of these variables and you did b, c, a, then this would be equal to b squared plus c squared plus a squared. And so you can see that these are equal. And so it will also be equal no matter how much or how you rearrange these variables. And so that's why this is considered a symmetric polynomial. But now if we were to consider this example using the same variables, let's say this is equal to ab plus c. Well then, if we were to switch it around, let's say a, c, b, if we were to switch around these variables, the ordering, then we would get ac plus b. And so these are not equal. So this is why this is not a symmetric polynomial. So that is essentially what a symmetric polynomial is. It stays invariant under all these permutations. So now that we've talked about symmetric polynomials, we can now talk about power sums. So, actually, wait. So before we talk about power sums, we should go over one more thing, and that is the fundamental theorem of symmetric polynomials. And so the fundamental theorem of symmetric polynomials states that for any symmetric polynomial f of x1, x2, xn, we can always express it in terms of only the n elementary polynomials sk in n variables. Also, it states that this expression will be unique. So essentially what this theorem states is that for any sort of like any of these symmetric polynomials that you can think of that are invariant, they can always be expressed in terms of only the elementary symmetric sums. And this expression will be unique. So we're not going to go over the proof of this. It is pretty advanced, and we're also not going to dive too deep into this topic. It will be covered most likely in a later video. But this is just like a good piece of information to know so that you don't have to, panic that and think that, oh, what if there's like another way that we could solve this or another factoring of it. So now we can talk about power sums. So power sums, they're also known as Newton sums, hence the name of the lesson. So power sums. Power sums essentially can be defined as this. So let's say the power sum pk of a polynomial P is P which has, or actually let's just of a polynomial P is equal to the sum of the kth powers of its roots. So for example, let's say you have P of x, right? This polynomial is equal to x minus r1, x minus r2, so on, x minus rn, right? So then pk is equal to x1k plus x2 to the power of k plus x3 to the power of k plus all the way to xn to the power of k. So that is the power sums. So this is a really useful piece of information to know. This appears very often in math competitions where they could ask you to find some relationship between roots. So now how do we actually find the kth power sum, right? Like this is cool and all, but how do we obtain this if we just are given like the polynomial, right? So this is actually a very crucial part of the lesson. So I'm going to start with a simple case, so P1, right? P1 is just equal to S1 because it is equal to X, or wait, sorry, this is not X, this should be R. So R1, R2, R3, Rn. So this is going to be equal to R1 plus R2 plus all the way to Rn, right? This is really simple. But now for P2, we can notice that it's already starting to differ from the symmetric sums. So how do we obtain this in terms of the symmetric sums, right? So if we were to consider S1 squared, right? S1 squared is equal to R1 plus R2 plus Rn. Right? So you notice that immediately that these will form the power sums, right? But we also have these sums, which are, if you remember, these are the second symmetric sums, right? So then, since there are two of them for each permutation or each combination of two variables, this is equal to P2, as you can see from this, plus 2s2, right? So then we get that P2 is equal to S1 squared minus 2s2. And actually, I'm also going to write this as P1 S1 minus 2s2, and you'll see why in a second. So now let's go to P3. I'm just going to write out what it simplifies to, but if you want, you can double check the algebra yourselves, just so you can, feel more sound. And so this is so P3 is equal to P2s1 minus P1s2 plus 3s3. And you guys might be noticing a pattern here, right? And it's that PK is going to be equal to pk minus 1 s1 minus pk minus 2 s2 plus blah, 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 and then it's always going to alternate the plus minus sign. So it's going to start with minus and then go to plus and then minus and then so on. And then the last term will be ksk, and it will depend on whichever sign it lands on. So that's why I just wrote plus minus here. And so this is sort of like the general formula for expressing the kth power sum. And so you can see that this is like a sort of like, maybe I guess it might seem kind of hard to memorize, but here's like a sort of like simpler way that I like to think about it. So imagine that you start from the first term, right? You start with pk minus 1, so the power sum right under the one that you're right below the one that you're trying to find, and then so you multiply that with s1. And you're going to keep doing that. You're going to go down from pk minus 1 to pk minus 2, pk minus 3, all the way to p1 and then k. So that's going to be the pattern for the power sums. And then with s, it's the opposite. So you're going to start from s1, and you're going to increase by 1, increase by 1, increase by 1, all the way until you reach sk. And so then that creates the relationship. So the first term, just to summarize, you start with the highest and then you decrease by 1, and then the symmetric sum, you start from the lowest and you increase by 1 until you reach the highest. And so that is basically power sums in a nutshell. But you might also be noticing something that seems to be off, or like an inconsistency, right? And that is, what if the number of variables of this polynomial p of x is less than k, right? What if k is greater than n? So that means that there are n variables, but k is greater than n. So how can you find sk, right? Sk, you can't express the k symmetric sum, elementary symmetric sum, if you only have n variables. That just doesn't make sense, right? And so there is actually a solution to that. So this is what happens if n is less than k. So I'm just going to write down the formula again. This is going to be equal to pk minus 1 s1 minus pk minus 2 s2 plus all the way to plus minus. Obviously, it's going to alternate again until you reach sn and then pk minus n. Pk minus n, k minus n. Here we go. So obviously, since k is greater than n, then k minus n is going to be positive. So this will be like a real number. It's not going to be like doesn't exist. So this is like the formula for if n is less than k. So there are fewer variables than the kth power sum. And so you guys, if you want, you guys can test out a few examples with this, and just to see it works and convince yourselves that it works. And so yeah, that is pretty much everything for this video. As I mentioned before, that these power sums are very useful in competitions, because a lot of competitions, they'll ask you for some relationship between the roots, like, oh, find the sum of the roots, or like find some sort of like manipulation, or some like expression involving the roots of the variables of some polynomials. And so by knowing this, which you can find the power sums using these symmetric sums, which can be found using Vieta's formulas from the polynomial. That means that if you're given a polynomial and you want to find some relationship between the roots, obviously this is a very powerful formula to have. So yeah, that wraps up today's video. Thank you guys for watching.